Welcome. In this video we are going to look at two important concepts of group. One is the center, another is the centralizer of a group. And here I have a happy little group for you. Inside it contains all beautiful elements of the group. And we also have a group operation. And with that group operation, a group satisfies four group axioms. Commutativity property is not included. That means we may have some element, some pair of elements, and if it can give this element, and if you change the order, it may produce another element. So this may happen in a group. Commutativity property is an extra feature. A group may have that property and it may not. And if two elements commute with each other, that means if we change the order, it doesn't matter, they give the same element, then we say these two elements commute with each other. And if we have some special element that commutes with every element of the group, it doesn't matter if we change the order, they will produce the same element. So this is a special element, it commutes with every element of the group. Now we are going to collect all such elements. Suppose these are those elements which commute with every element. Then we are going to put them in a box and call it the center of group. So in center of group we have elements which commute with everything of the group, and don't think that we have placed this one means this is no longer an element of this one. This is just another home for these elements. These elements belong to this one and this one. This is our primary group. So this is our center. Center is a set containing all such elements which commute with everything of the group. It commutes with every element of the group. And for any group, we know identity commutes with every element. So identity must remain in a center. Center is not empty. Next, we will see the centralizer. So these elements are in our group. Let me put them. So center of a group is clear. Now for centralizer, we have centralizer of each element. We have centralizer of this element, centralizer of this one, and centralizer of this one, and centralizer of this one, and so on. We have centralizer of each element. For centralizer of this one element will remain in this set if this commutes with only this element. And it need not to commute with any other element. It may commute, it may not. So if this also commutes with this one, then put this one also here. And if this element commutes with this one, put this one into here. So we have centralizer of elements. Centralizer of an element, the set of all those elements which commutes with that element. It need not to commute with anything else of the group. So we have centralizer of each element and center of a group. Next we are going to see some observations, examples and theorems. So the center of a group is a subset of that group, and it contains all those elements which commutes with every element of the group. And in set notation, this is the symbol for the center of group, and we have all such elements of group G which commutes with every element X of group G. So this is our center. And we have some observations. See, first one is identity always belongs to center of a group because identity commutes with every element of the group. It happens for every X in group G. And second observation is we have if G is abelian, if our group is abelian, that means every element of the group commutes with every other element, then its center is the whole group G. And for example, we'll see some of the examples of the center of some groups. Note, if group is abelian, then center of its is not very interesting. Things get exciting if group is non-abelian because we have something else from the group which is center of that group. And for first example, we have one non-abelian group. We have already seen D4, and in that group we have two elements. One is identity, which is R0, and R180. We have seen the KLA table of the group, and R0, R180 commutes with every element of that group, and none of the other elements commutes with every element. So center of D4, this is our group. Center of D4 contains R0 and R180. And if our group is GLNR, the general linear group of order n with real entries, it contains all those matrices, square matrices of order n whose determinant is non-zero, and this group is also non-abelian, and its center is all scalar matrices in GLNR. Scalar means this is a diagonal matrix and all diagonal elements are same, and note other elements are 0, and this A should be non-zero because the determinant of this matrix is A to the power n, and if A is 0, this matrix does not belong to GLNR. So the center of this matrix, center of this group is the set of all scalar matrices in GLNR, and center of D4 is R0 and R180. Next, we will see a theorem on the center of group. See, the center of a group is not only a subset of that group, it is a subgroup of that group. That means under the operation of group G, it will also satisfy all four group axioms. It is a group itself. And next we will prove this one, that the center of a group is a subgroup. So first we will show that the center of a group is non-empty. Actually we are going to use the two-step subgroup test. Use the two-step subgroup test. So two-step subgroup test says if a subset is non-empty and it is closed under the operation and it contains inverse of every element, then that subset is a subgroup. First, ZG is non-empty. Non-empty. And clearly note E is the identity of group G. Ex equals to xe for all x in group G. E is the identity. So identity commutes with every element of the group G. That implies identity will always remain in the center of group. So a center of a group is always non-empty. Next, ZG is closed under the operation of G. Under the operation of G. That means take any two elements, let A be in the center, we have to show its product also in the center. That means if A commutes with every element of the group, B commutes with every element of the group, then its product will also commute with every element of the group. Let X be any random element of group G. We have to show AB X is same as X times AB. This is same as A XB. Sorry, first we will apply associativity. Parentheses can be put anywhere. Parentheses are redundant by associativity property, and this can be written as XB since B commutes with every element. B commutes with the element X, so Bx is same as XB. Now we can again apply associativity. Parenthesis, we can put parenthesis here by associativity, and this is same as XAB. Again, since A is in the center, A commutes with X, and we can put parenthesis here by associativity. So we have arrived here, we have started from here. So this one is same as this one. So AB commutes with X, and X is any arbitrary element of group G. So AB commutes with every element of the group. Hence, that implies AB is an element of the center. Next, we will show that the inverse of every element in center is also in the center. Next, we will show that inverse of each element of center is also in the center of group. Let A be any arbitrary element in the center, that means A commutes with every element, so X equals to XA for all X in the group. Let us multiply A inverse in both sides, A inverse, and here we also have A inverse. We can do that because we are doing the same thing in both sides. Now we can use the associativity property to group them. So we have this one, and what is A inverse A? This is identity, so identity times this one is X A inverse, and here we also have A inverse X because this is identity, and this happens for every X in group G. So A inverse commutes with X, that implies A inverse belongs to ZG, the center of group. So we have proved that center of a group is not only a subset, it is also a subgroup of that group. We have the centralizer of an element, the centralizer of A in G, and the definition says the centralizer of A, this is the notation for the centralizer, and this is centralizer of A. Definition says it contains all elements X, so that XA is X, and obviously X is an element of group. So if X commutes with A, then we have X in centralizer of A in G. And we have few observations here. Observations. Note, first one is centralizer of identity is whole group G, because every element commutes with E. So centralizer of identity is a whole group. Second, if A an element of the center of group G, that means A commutes with every element, then also we have its centralizer the whole group, because A is in center, A commutes with every element, so every element will remain in because they commute with A. Third, if G is abelian, so every element in the center C of A is G, and this happens for all A in G. Next, ZG is the intersection of all centralizers, and this for all A in G, because in centralizer of A we have every element which commutes with A, and see all centralizers find the intersection, find the common element, that means that element will commute with every element, hence it lies in the center of the group. Next, let us see some examples. Here also, if the group is abelian, then its centralizer is not very interesting, because centralizer of any element is whole group. If group is non-abelian, then we have something else. If suppose group is D4, which we have already seen, then what is CR0? CR0 is whole group, because R0 is identity, and this is also same as CR180, because R180 lies in the center of D4. CR90 is the collection of all rotations, R180, R270, and this is same as CR270. And what is CH? H is horizontal flip. CH contains R0, R180, obviously, because they lie in center and they must commute with H, and we have H itself and B, and this is same as CB, and CD is same as CD dash, and which is R0, R180, D and D dash. And next, we will show that centralizer of any element is also not only a subset, it is a special subset. It forms a subgroup of that group, and the proof also uses the same techniques as in the center. This uses two-step subgroup test. Two-step subgroup test, where first one is CA is non-empty. And why? Because identity belongs to CA for any A in group G. Centralizer of any element, we have identity. And what about closure? If we have two elements, suppose G1, G2, with two elements in the centralizer of A, then its product also is in centralizer of A. That means G1, G2 will also commute with A, and which is clear. Note, G1, G2 A is same as G1, G2 A by associativity, and this is because of G2 lies in the centralizer of A and G2 commutes with A, and which is same as G1A, G2, which is A, G1, G2. This is because G1 commutes with A. So we have G1, G2, an element of centralizer of A. And what about inverse? If B is in centralizer of A, then B inverse is also in. We have to show this one. We have to show if B is in centralizer of A, then B inverse also is in centralizer of A. Note, we have B is in centralizer of A, so BA equals to AB. Now let's multiply B inverse in both sides. B inverse, B inverse. So here we have AB inverse and B inverse A, because B inverse B will cancel, and here we have B inverse. So B inverse commutes with A, that implies B inverse belongs to the centralizer of A. So center of a group and centralizer of any element of that group, they both form subgroup, and center of a group is a feature of a group, and centralizer is related to every element, centralizer of any element. So for this video, this much. Thank you.